Today, we're gonna start the probability and random process class. So this is the first week. That's why I wanna go for easily or slightly. So we will cover the basic theory of probability at first, and then we want to see some examples about that. So this is our outline. So here in chapter 2, we're gonna study about the probability theory. First of all, we want to understand how to specify the random experiments. And then in chapter 2.2, we would like to cover the axioms of probability, and then we will cover the conditional probability. After that, we want to study about the independence of events, and lastly, we want to see the sequential experiments. So among these stuffs, I want to go for the first item only in this class because this is the first week. So I want to do some slow starting, okay? So here we want to understand what is the sample space at first, and then we want to understand what is the events inside the sample space. So that is the basic concepts in probability theory. That's why I hope you understand these items fully during this weekend. And next Tuesday, we're gonna study about the axioms of probability and conditional probability at the time. Okay. So here we want to see some notions, okay? So first of all, E means random experiment. Suppose that we have some dice tossing. So this is our dice. It has the number 1, 2, 3, 4, 5, 6 inside here. And then we're gonna toss this one several times. That's called random experiment, okay? And S means a sample space. Sample space means the set of possible outcomes. Here we have 6 types of set of possible outcomes. That's why this is called sample space. Okay, and sample space is denoted by capital S. Okay, and small s means outcome. The outcome is the element of this sample space. Okay, and then we have some event. Event is kinds of our condition to select some elements from this sample space. That's why we said that this is subset of sample space. And then this is the set of the outcomes, and we have some conditions about this one. So most likely we will focus on the sample space and event. Okay. So sample space. Sample space can be defined as discrete sample space or continuous time sample space. So suppose that we are doing dice tossing as mentioned before, then we have 6 different types of the outcomes. 1, 2, 3, 4, 5, 6. Suppose that we are doing some coin tossing. So we have coin and it has head or it has tail. That's why we have discrete events just like that. Also, we have some continuous domain sample space. For example, height and weight and temperature. So height. So when someone asks me about my height, then I may say that, okay, my height is 173.65, 65, 65, and so forth. So we cannot specify the height exactly because it exists in continuous time domain. That's why I need to do something like rounding. So I just say that my height is 173 and that's it. So this is called rounding. By doing some rounding, we can convert this continuous time domain value into this discrete time values. However, the value itself is continuous time, a continuous domain value. That's why these are all continuous sample spaces, okay? And then we have another definition that is called event. So event called a subset of a sample space. This is defined as follows. That's why we can say just like that. Okay, among this coin toss result, we want to select only even numbers. Then we can say that we have 2, 4, 6. So this is a subset of capital S. This is called E, and E is a subset of S. Okay, and in continuous time domain, event can be, for example, okay, among these given set, I want to find some statistics where the height is between 150 and 170. So the height between 150 and 170. So in this case, this is the condition into a continuous time domain. So this is called continuous event. Okay. Also, the event can be empty set. So this is called null event. So in this case, we have no outcome. For example, within this tossing course, within this dice tossing, we want to find the case where we can see number 7. But number 7 is not existing here. That's why there's no chance to see number 7 in this case. That's why the result and the set itself becomes empty set. That's why we can denote it by empty set. Element event means the every single outcomes in sample spaces. Okay, it's very easy and straightforward. So here we want to understand the sample space and event in this given examples. That should be enough for our first class. Okay, so let's look at one by one. Should be very easy. So here we want to select a ball from an urn, and then the ball numbered 1 to 50. It means that in an urn we have 50 number of balls. So that's why the sample space is the 15 number of balls here. Okay, and then we wanna select even number of balls. It means that we wanna select the balls. Those are all even. So 2, 4, and so forth, and 50. Okay, so very easy, right? So we are finding SA and A, sample space and event. Okay, so let's look at another example. So select a ball from an urn containing ball numbered 1, 2, 3, 4. It means that in an urn we have 4 balls. In a 4 balls, the first ball and second balls are black. Those are black balls. And third and fourth balls are white. So this is our sample space. So it can denote it as follows. The first ball, second ball, third ball, and fourth ball, and the colors are black, white, and white. Okay, so this is our sample space. So among this given sample space, we have to select our interesting event. So here our interest is on the white ball. So that's why we don't need to worry about this one. Okay, and then we have another condition here. So it should be even numbered. That's why we have to select this one. So only this element is our interest. That's why this becomes event. And then in next example, we are tossing a coin 3 times. So that's why we can see head or tail 3 times. That's why head, tail, head, tail, head, tail, head, tail, head, tail, head, tail, tail, head, tail, and tail, tail. So here we have 8 different number of cases because we have 2 different cases for 3 times. So it becomes 2 to the 3. So that's why it is 8. So among this given sample space, all possible cases, we have to select our interesting event. So our interesting is the case where the 3 tosses give the same outcomes. So here, this is our interest. This is not, 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 this is not. This is our interest. That's why we have 2 interests in this given sample space. And these 2 elements becomes our elements in our event set. So this is our event set. So similarly, we are toss a coin again, 3 times again, and note the number of the heads. So if we toss a coin 3 times, we may not be able to see the heads because of the case where we always get tail every single time. So that's why it becomes 0. Or we can see the head only 1 time. So this is 1. We can see the head only 2 times, or we can see head every single time. So it's 3. So this is our sample space. Among this given sample space, we have to find our interest. So here our interest becomes the case where the number of head equals to number of tails. So we need to draw some tables about that. So this is head, this is tail. So as you can see here, this can be 0, this can be 1, this can be 2, this can be 3. So if we are not looking at head at all, then we saw the tail 3 times entirely. If we saw head 1 time, then we may be able to see the tail 2 times. That becomes 2. If we saw head 2 times, then we may be able to see the tail 1 time only. If we see head 3 times, then we may not be able to see the tail at all. This becomes 0. So every single time, they are not same to each other. So 1 and 3, not same to each other. 1 and 2, not same to each other. 2 and 1, not same to each other. 3 and 0, not same to each other. That's why we have nothing. So our event is empty set. So it's very easy, okay? So up to now, these are all the case for the discrete case, because our sample spaces are all discrete values, right? From now on, we want to see the case where our sample spaces is continuous. So here we are talking about continuous domain, okay? So here, pick a number at random. So there's no restriction about the integer or something like that. So this is just a real number, okay? Real number between 0 and 1. That's why this is a real number between 0 and 1. So we can denote it as follows. When you use this one, it means that we will include 0 and 1. When you denote this one as just like that, then it means that we will not include 0 and 1. Anyway, in this case, we are including 0 and 1 just like that. That's why we can denote it as follows. Okay, so among this given sample space, we need to find our interest. So here we define our interest as follows. So our interest is that the number selected is non-negative. It means that it should be always positive or 0. So here you can see that they are all positive, and it also includes 0. That's why our interest is exactly the same with our sample space. That's why we can denote it as follows. A equals to S, and that's it. For next case, we are looking at some real life example. So in this example, we have one given computer memory chipset. So when you buy some computer memory chipset, it can be in malfunction immediately. So that's why the lifetime can be 0. If you buy something, it is already broken, then we cannot use this one at all. That's why the lifetime is 0. That's why it starts with 0. And if this is very robust and we can use this one forever and ever, then it can go to infinite. So the time is just larger than equal to 0, okay? And then it can go to infinite. And in specific environment means that if we are in universe or space, then in that case we have no gravity and no airs over there. That's why it should be very clean. That's why you have no chance to be broken at the time, at the space. That's why we can use this one forever and ever in universe, maybe. That's why in specific environment we can use this one forever and ever. That's why we have no restriction in terms of upper bound. So we can define our sample space just like this one, okay? And then here in this continuous domain, we can define our interest as follows. The chip lasts more than 100,000 hour, but fewer than 150 100 hours, 1500 hours. So then we can define just like that. The time should be larger than 1000 and 1000 and less than 1500. Then it can write down just like that. This is typo, so you can look at just like that. So we can write down just like this one, okay? So as I told you before, this means that we are not including 100. We are not including 1500. We are not including 1000. We are not including 1500, okay? So it's very easy and straightforward. So we want to see more examples about that. So now we are picking multiple number of random variable, okay? So now we are picking 2 random variables, and both of them should be between 0 and 1. That's why we are picking x and y, and both of them should be between 0 and 1, just like that, and that's it. So among this given sample space, this is the entire sample space, and then we have to select our interest. So our interest is defined as follows. Our interest is the 2 numbers differ by less than 1/10. It means that the difference between the x and y should be less than 1 over 10. It means that, so that's why we have to write down this one at first. Our given data should be in our sample space at first, and then their difference here should be less than 1 over 10. So it means that x can be bigger than y or y can be bigger than y. That's why we don't know what is bigger than the others. That's why we have to take the absolute value just like that. In our previous example, we did not express this one before because they already bounded in sample space. Here, this is already within here. That's why we don't need to write down this one anymore. Again, so this one is already this one. That's why we don't need to write down that A should be A should be a subset of S. We don't need to write down that comments in this case. Here, this is empty set. That's why this is already inside here. That's why we don't need to write down that anymore. Here, this is already inside here. That's why we don't need to write down that A is a subset of capital S. Here, that's the same. So this is already subset of this one. That's why we don't need to write down that A is a subset of capital S. We don't need to do that. But in this case, we have to write down this one because only this one cannot say that this A is a subset of capital S. That's why we need this definition. Okay, you need to be careful about this one. And now this is very similar, but this is a little bit different. Here, as you can see here, we have to pick random variable x. This should be between 0 and 1. This is the thing what we did before. And then we pick another value y that should be between 0 and x, not 1. That's why this is a different one, right? So here this was 1, now this is x. This is the different thing between these two examples. So here we can write down this one. This is also correct. However, we can convert to the right hand side, which says that y is larger than equal to 0, and then x is larger than y equals to y, and then number 1 is larger than equal to x. We can write down this one. So both of them are same to each other. That's why you can write this one just like in left hand side or right hand side. It's up to you. So now we define our sample space, and then now we have to define our interest. Our interest is the same with the first one. Okay, our interest is the case where the two numbers differ by less than 1 over 10. It means that we have to write down this one again, and then we have to write down our condition again, and that's it. Okay, so this is very easy and straightforward. Now you can do the sample space definition. Sample space means that all possible cases you can get in these experiments. So during this experiment, you will see a lot of cases. So if you gather all possible cases in a set, that is called sample space. In event, you have to select some of them where you have interest on it. That's why A becomes a subset of capital S. Or A can be empty set, A can be entirely same with capital S. That should be the special cases. Those should be special cases. However, A cannot exceed the capital S because A is an entire sample space. Okay, you have to remember about that. And now it's time to look at the sets theory. It is very easy, and you may study this one during your high school ages, first grade. Okay. So first of all, you may know what's the union, right? So union means that it can be A or it can be B. So you can do both. That's why this is or notation. Okay. You have to gather all the element where the element can be an element of A or it can be an element of capital B. Okay. Intersection means that the X should be an element of A as well as an element of B. Then you have to select the X entirely, then that's called intersection. So in this case, so this is the intersection. This part can be a subset of A as well as subset of B. That's why this is intersection. So now we have to look at the mutual exclusion. It means that if A and B has no intersection, okay, they are absolutely different to each other. So for example, this is even number, this is odd number, then there's no overlap. Then we can say that this is mutually exclusive, okay? Or this is called disjoint, or there is nothing for the intersection. We can write down these three types of explanation in order to explain mutually exclusive. The next one is a subset. Subset means that B include capital A. So then we can say that A is a subset of capital B. When A is an element of A implies X is the element of B. Okay, so then we can say that A is a subset of capital B. Complement. Complement means that we will get all thing which is not in capital A. So this one is called complement. So this is A, then the others are all complement of A. Okay, you have to remember this one. So now we will look at the basic theory properties of set operations. So the first one is a commutative law, which means that we can swap A and B. We can swap A and B. Okay. So that's called commutative law. It's very straightforward. That's why let me skip the proving about this one. And then the other one is associative law. It means that when you have union and union, and then there is a bracket here, then you can move these braces to here, okay? Or you can have intersection and intersection, then you can move these braces to these ones, okay? To these positions. Distribution law is that this is union, this is intersection. Then you can distribute A union into here and into here. That's why you have A union B, A union C, and then finally you have intersection, okay? In a similar way, you have A intersection B union C. Then in that case, you are put this A intersection inside this brace. That's why you can move this one and you can move this one. Okay. Then you have this one, and then you have this one, and then you have a union between there. Okay. The last one is De Morgan's rule. So this is very famous. So you may study about this one during your high school ages. So here, when you have A cup B and complement, and then you can move this complement inside here. So that's why it becomes A complement, B complement, and this becomes cup, just like that. That's why you have this result. Okay. In a similar way, when you have A cup B and complement, then in this case, this can be inside and inside. That's why you will get A cup, A complement and B complement, and then the cup becomes union. Okay. That's why, this is not cup, this is head, okay? This is head. So then you can get this one, okay? This is head. Okay? So you can see this property easily because you may know this one already during your high school ages. So in this first week class, this is just kind of warm-up class. That's why we are not go to the details. We just cover the basic definitions of sample space and events, and then we are looking at the basic set theory inside there, and that's good enough for our first week. For our next week, we're gonna see the axioms of probability and conditional probabilities here. So this is our next Tuesday class. For our next Tuesday class, this is for our next Thursday class. So then we are done for the chapter 2, and then for the next week we will go through one by one from the time. Okay. Thank you for listening to this presentation, and let's meet together again on next Tuesday. Thank you.